Hi guys, I'm going to talk about water potential and just revisit that again. And I'm going to then go through a couple of different practice problems to make sure that you're comfortable with how to solve them. So the first thing that I just want to revisit is osmosis. Remember that osmosis is the movement of water across a membrane from area of high concentration to low concentration. So high concentration of water to low concentration of water. Okay, you can also sometimes see that um, osmosis will be described as water moving to areas of high solute concentration. So you could see that appearing in different ways, but it means the same thing. So if we're looking at this diagram on the right here, you can see I have a high concentration of water on this side, very low solute. And over here I have a lower concentration of water relative to a higher amount of solute. Okay, with the yellow being the solute and the little blues being the water. Okay, and then water is going to move this way. The barrier is too small, so the solute is not able to move. So the water is going to move to equal out the concentration as best it can. So when we're talking about osmosis, though, we've never really talked about why water moves. Okay, we just kind of says it. We just say it does. So let's talk about why it does. Water moves based on water potential, and water potential is the potential energy of water. And basically, this is a measurement that combines the amount of solute in a solute concentration in a solution, but also takes into account pressure. So if we look at the picture on the right, you can see that there is some type of attractive force between these water molecules and the solute, okay, because this is dissolved. So when these molecules are interacting with each other, that creates less free water molecules that can move around. So on this side, you have significantly less water molecules that are free to move around easily. On this side, you have lots of free water molecules, okay, that aren't associated with solute in any way. So water, when it has free, it has a lot of potential energy to move around. When water is kind of in close proximity to solute, okay, it's kind of stuck and can't really move around, so it has very low potential energy. So water potential and the way that this impacts osmosis is that water will flow from regions of high water potential to regions of low water potential. So this side has high potential. Okay, so this is high water potential, and we use the letter psi to denote water potential. And this area over here has a much lower water potential because we have less free water molecules. So as a result, water is going to want to cross the barrier this way. Okay. We use the equation psi equals solute potential. Okay, so how much solute? And then we can use this little equation to calculate solute potential as well. Negative I, so the ionization constant. So how many ions are we forming? So with something like salt, that would be 2 because you form sodium and chloride. With something like glucose, it would be 1. We don't really deal with anything that forms 3, so it's either 1 or 2. C would be the concentration, the molar concentration. R is our pressure constant, which is always going to be this value right here. And then T is going to be the temperature in Kelvin. So that's 273 plus the degrees Celsius. Pressure potential is physical pressure on the solution. In most cases, though, in an open beaker, your pressure potential is actually going to be 0, okay, because there isn't, so the solutions typically that are exposed to, that are open, so like an open beaker, an open solution, your pressure potential is going to equal 0. However, within a cell, you have something called trigger pressure. And this is going to be in cells with cell walls, okay, because you have that like physical barrier. So in cells with a cell wall, you're going to have pressure exerted from the plasma membrane against the cell wall and the cell wall against the plasma membrane. So you can only fill up that cell so much. in an animal cell, essentially, if you get too much water rushing into an animal cell, the cell will lyse. So that we really don't get the turgor pressure the same way we do in a plant cell or another cell with a cell wall. So that's just something to consider. So let's go through and solve a couple of these problems. So if a cell has a pressure potential of 3 bars, and bar is just a unit of pressure, and a solute potential of negative 4.5 bars, what is the resulting water potential? So the water potential, remember, is psi equals pressure potential or solute potential, or the other way around. So your water potential here is going to equal 3 bars plus negative 4.5 bars, and that is going to equal negative 1.5 bars. Okay, so that is going to be the resulting water potential. Typically, your water potentials are going to be on the negative side, usually because of the solute potential. And solute potential is always going to be negative or 0 if it's pure water. Okay, so let's go on to number 2. So the cell from question 1 is placed in a beaker of sugar water with a solute potential of negative 4 bars. So let's figure out what the water potential of that solution would be if our solute potential is negative 4. So water potential equals the pressure potential plus solute potential. Because this is in a beaker that's open to the atmosphere, our pressure potential is going to be 0. And then our solute potential is negative 4 bars. So my water potential, and then I'm just going to label this solution, is going to equal negative 4 bars. Up here, I found out that my water potential of my cell is negative 1.5 beakers, so this equals the water potential of the cell. I find it very helpful to draw pictures whenever I'm trying to figure out what's going to happen. So I encourage you to do the same. So here's my cell. My cell is negative 1.5 bars. My solution is negative 4 bars. Water moves from high water potential to low. So if it's moving from high water potential to low water potential, that means that the water is going to leave the cell. Okay, so the water will leave the cell. Okay, let's look at the next one. So the original cell from question number 1 is placed in a beaker of sugar water with a solute potential of negative 0.15 megapascals. Okay, we know that 1 megapascal equals 10 bars. So sometimes you might see other units. Okay, it's still a pressure unit. It's just something that's a little bit different. So it really just kind of depends. Typically, I believe we see bars on the AP test, but you never know, so you just want to be prepared for anything. So we need to do a little conversion. Okay, so if we know that our water potential equals our pressure potential plus our solute potential, our pressure potential equals 0, and our solute potential is negative 0.15 megapascals. So my water potential of the solution will equal negative 0.15 megapascals. To compare this to my original cell, I do want to be able to convert. So let's convert this to bars. So in order to convert this, you need to use a conversion factor, which you are told the 1 megapascal equals to 10 bars. So when I do this calculation, I should get negative 1.5 bars for my solution. So let's draw a picture of what we have going on. Here's my solution. My solution is negative 1.5 bars. My cell, remember, is also negative 1.5 bars in terms of its water potential. Because they are both the same, we are going to be in equilibrium. So you will have no net movement of water. But keep in mind, water and all molecules are always moving, so you are going to have some movement in and out, but no net movement. Okay, let's look at the next one. So the value for the value for water potential in root tissue was found to be negative 3.3 bars. If you take the root tissue and place it in a 0.1 molar solution of sucrose at 20 degrees in an open beaker, what is the water potential of the solution? In which direction do you think that would flow? So let's go through and do this calculation. So we know that our root tissue is negative 3.3. We need to figure out what our solution is. So the goal here is to figure out the water potential. Remember that the water potential of my solution is going to equal my pressure potential plus my solute potential. My pressure potential, we're in an open beaker, so that's going to be 0. And then I'm going to have to figure out what the solute potential is. So let's come over here for a second and we'll calculate the solute potential. So we're using the equation negative I. Okay, so this is a negative value based on the ionization constant, based on the molarity, our pressure, as well as value, and so this equals negative. Our I should be 1. Okay, we're dealing with sucrose. Sucrose is not ionized, so there will be 1 molecule. The more molecules you have, the more negative it's going to make this, because there's going to be more solute for the water molecules to kind of latch onto and form protective forces with, which should reduce your water potential. Okay, so negative 1, our concentration is 0.1 molar. Our constant is 0.08. And this is something that's always provided to you, so you do not need to memorize it 3-1. By the time you're done doing these problems, you probably will know it. It is bar liter per mole K. And remember that moles over liters is going to be your molarity, so that'll help us cancel that. And then 273 plus 20 degrees Celsius is going to give us our K. We'll just leave this K. So we're adding them together. Okay, so we can cancel our units. Okay, so remember that M essentially equals moles over liter, so I can cancel this. My Kelvin will cancel. Okay, and I'm going to be left with actually just bars for my solute potential. Okay, if I multiply this out, this should equal negative 2.4 bars. Okay, so let's come back to our equation. Our solution water potential equals the pressure potential plus solute. We're in an open beaker, so pressure equals 0, and my solute equals negative 2.4. So the water potential for my solution should equal negative 4 bars. Okay, let's draw a picture. 2 bars for the solution and put my cell in here. My cell is negative 3.3 based on the question information. Water flows from high water potential to low water potential, which means that the water is going to enter into the cell. Okay, watch the negatives. They can be a little tricky. Okay, let's look at the next one. Sodium chloride dissociates into two particles of water, sodium ions and chloride ions. If the solution in question 4 contained 0.1 molar sodium chloride instead of 0.1 molar sucrose, what is the water potential of the solution, and in which direction would the net water flow be? So let's go through and think about this. Excuse me. So our solute potential is going to change. So remember, we had an ionization constant of 1 last time. So this time, I'm actually going to have an ionization constant of 2. So instead of being 1, it'll be negative 2 times 0.1 molar times 0.89. Okay. No, so 5 liter mole, okay, times 293. And when I multiply this out, my solute potential, okay, is basically double. So instead of it being 2.4, now it's 4.8. So my water potential equals pressure potential plus solute potential. So the solution is 0 plus negative 4.8. So total equals negative 4.8 bars. And note, okay, remember the solution has a huge impact on water potential, right? The more molecules of solute you have, the less free water you have, which means you're going to have a much lower water potential, okay? So water is going to move to where the solute is, okay? So let's look at what this looks like. And my solution is negative 4.8 bars. My cell is going to be still negative 3.3 bars. Okay, and this is going to completely change how water moves. Okay, instead of moving into the cell, okay, now my higher water potential is the cell. So in this case, instead of water coming into the cell, water is actually going to leave. It is going to go from where it's highest, negative 3.3, to where it's lowest, negative 4.8 bars. So water leaves cell. Okay, there's a net movement of water leaving the cell. Okay, and that really just has to do because you have more solute molecules. Okay, sodium chloride ionizes into 2 molecules, which doubles our solute potential. Okay, a plant cell with a solute potential of negative 7.5 bars keeps a constant volume when immersed in an open beaker solution that has a solute potential of negative 4 bars. So what is the cell's pressure potential? So for this one, we want to be thinking about how could we keep this at equilibrium? Okay, so one thing we want to think about is equilibrium. The pressure of the solution is going to equal the water, the water potential of the solution is going to equal the water potential of the cell. Okay, that's what we discovered up here whenever we did this problem. There was no net movement because these two were equal. So that's something that we can try to find here. So let's figure out how we could do that. So I'm just going to kind of draw a picture. Our goal here, we know that the open beaker solution has a solute potential of negative 4 bars. Remember, okay, so the solution equals pressure plus solute, and at this point you probably know pressure is 0. So the water potential of our solution is going to equal the solute potential, which is negative 4 bars. So our goal here is to get our solution negative 4 bars, and our cells also to be negative 4 bars. Okay, so that's where we're trying to get to. So we need to figure out what the pressure potential of the plant cell needs to be in order to attain this. So let's go through and figure out how we can do that. So if the solution equals negative 4 bars, and I want my cell to also equal that, let's go through solute. I know what my pressure potential, I know what my solute potential is. I do not know what my pressure potential is. Oops. So negative 7.5 bars. Okay, so, and this is going to equal what my cell, or excuse me, this is going to help me figure out my pressure. So if I do the math here, okay, my pressure potential in order to establish equilibrium, negative 4 bars all around, would have to equal, oops, that would have to equal 3.5 bars. Okay, so there has to be 3.5 bars of pressure between the cell wall and the cell membrane. This is going to keep this cell from gaining excessive amounts of water. So if there was no pressure, it would be negative 4 bars in solution, and you would have negative 7.5 bars of just based on solute potential inside the cell, which would mean that water is trying to flow into the cell very rapidly. Because this plant cell can only have so much water coming in, there's going to be this pressure potential that's kind of keeping some of that water out, okay, and that's going to be this 3.5 bars. Okay, so let's look at the next one. At 20 degrees, a cell containing 0.6 molar glucose is in equilibrium with its surrounding solution containing 0.5 molar glucose in an open container. What is the cell's pressure potential? Okay, so let's go through and figure these out. So this one you have to solve like pretty much everything for. So let's first start with the cell. Okay, so let's figure out the cell's solute pressure. Or excuse me, solute potential. Ooh, I've been going too long. Okay, so this is going to be negative ICRP. And this is going to be negative 1. We're dealing with glucose. Glucose does not ionize. 0.6 molar times 0.831 liter full K times 293. This is what happens when you have 20 plus 3. And this is going to be negative 14.6 bars. Okay, let's look at the solution. Negative ICRP, negative 1. We are working with 0.5 molar in solution times pressure times 293. This would equal negative 12.2 bars. So let's figure out the total water potential. Okay, so the total water potential for my solute, actually, we'll do Excel first. So the water potential for, actually, it's on calculate. like that. Okay, so let's look at our solution. So the water potential for my solution is going to equal pressure potential plus my solute potential. We know the pressure potential is 0. We are in an open container. So the water potential for my solution will equal 0 plus negative 12.2 bars. Then negative 12.2 bars for my final answer. Okay. My cell though, okay, so let's think about my cell. So the water potential of my cell is going to equal the water potential of my solution at equilibrium. So that means that negative 12.2 bars equals the water potential of my cell, which is going to equal solute potential plus the pressure potential. So we know that the solute potential equals negative 14.6 bars. So negative 12.2 bars equals negative 14.6 bars plus my pressure potential. Okay. And that would mean that my pressure potential has to equal 2.4 bars. Okay, and then go to ether for a second. Okay, so if my solution is 12.2 bars, okay, if only based on the solute potential, my cell would be negative 14.6 bars, which means that water would flow from the solution into the cell. Because this was at equilibrium, you need to have some pressure keeping some of that water out. Okay, and that pressure, when added to the solute potential, also make my cell 12.2 bars for total water potential, which should keep us at equilibrium. Okay, no net movement. Okay, last one, guys. So at 20 degrees, a cell with a pressure potential of 3 bars in equilibrium with its surrounding of 0.4 molar solution of sucrose and an open beaker. So what is the molar concentration? This one you kind of have to do a little bit of backwards work. Okay, so let's look at our solution here first. Hold up one second. So solution, the water, or the solute potential is going to be negative ICRT. Okay, because we know that we have a 0.4 molar solution. Negative 1, we're dealing with sucrose, which is not ionized. Molar concentration is 0.4 molar. Oops, almost got it. Bar liter mole. Okay. Now we're at 20 degrees, so 296. Okay. And we solve this is going to equal negative 9.7 bars. Okay, our total water potential for our solution equals the solute potential plus pressure potential. Hopefully at this point you realize that we don't have to concern ourselves with pressure, so that means that our water potential is going to be negative 7 bars. Okay, so at equilibrium, my cell equals my solution. So the water potential of my cell should equal negative 9.7 bars. And remember that this is going to equal the pressure potential plus the solute potential. So we know that the pressure potential is 3 bars. bars. What we need to figure out is the solute potential. Okay, so my solute potential, if we do the math, is going to equal negative 12.7 bars. So let's figure out if we can figure out what the molar concentration is now. So now we have our solute potential. We can use this equation, negative I CRP. We know that this should equal negative 12.7 bars. Okay, we're dealing with one ion, so negative 1. This is what I'm trying to figure out. So 1 bar. Yeah, okay. And times 293. Okay. If I solve for C, okay, or just solve for everything else, negative 12.7 bars equals negative 24.3 bars times C. Okay, divide by this. Okay, that'll cancel bars and will give me a 0.52 molar solution as my answer. Okay, so the cell would have to have, for equilibrium, to have a 0.52 molar concentration of sucrose in it in order to keep equilibrium with a 0.4 molar solution of sucrose in an open beaker. Please bring any questions you have with you next time to class, or make an appointment with me to go through this. I'm sorry that this was a little bit longer, but I think it was good to kind of be able to go through and solve these problems together. Have a really good day, guys, and I will see you next time we have class.